Hello everyone. So in the previous two videos we have covered the basics of set theory and how to do the basic operations on set theory. We have covered the subsets and the De Morgan's law. Now in this video we are going to discuss about sigma algebra. So sigma algebra is a very important concept in probability theory and measure theory, and we are going to use it to define a lot of important things like probability space or measure space. So let's see what a sigma algebra is. So let's say we have an arbitrary set omega. So we have any set omega. Omega can be anything, and the collection of subsets of omega such that it satisfies these three properties. Such a set is called as a sigma algebra on omega. So let's say there is a subset A1 which which is a subset of omega, okay, and let's say there is another subset of omega which is A2. Now let's say I have to define a set of sets such that f is, let's say, A1 and A2, and let's say it has a few more elements other than A1 and A2. We're going to come to that later. So this means that first of all, this f, which is a set of subsets of omega, this should be non-empty. And now let's see what the second property is. So the second property is that it should be closed under complement. So what does closed under complement means? Closed under complement basically means that it follows closure property for the complement of its elements. So for example, let's say we have a subset A, which is a subset of omega, and A also is contained in the sigma algebra F. So if F is a sigma algebra, if A complement also belongs to F, so this is the closure property. So any subset which is present in the sigma algebra F, if this is present, then A complement should also be present in this sigma algebra. So this is the closure property of under complements. And the third property is that it should be closed under countable union. So what's a countable union? A countable union is nothing but a union of some sets. So let's say we have few sets. A1 is a subset of omega, A2 is also a subset of omega, and A1 and A2 belong to F, the sigma algebra. So A1 union A2 should also belong to F. This is the closure property for countable union. Similarly, we can extend this to multiple number of subsets. So for example, we have A1, A2 till AK, all are subsets of omega, and all of these are also contained in the sigma algebra F. They also belong to F. Then union of all of these AIs, union of this should also be contained in the sigma algebra F. Okay, now let's see a few examples and evaluate whether we can determine whether a function a set F can be called as a sigma algebra on omega. Okay, I think the example will make it more clear. So let's say we have an arbitrary set omega containing three elements A, B and C. Okay, and let's say we have defined a set F1 containing these two sets. So we have, this is the null set, which is an empty set. You can also define it as phi, and this is the same as that of omega, so you can define it as omega in this case. Okay, so we have to check whether f1 forms a sigma algebra on omega. So let's see if f1 is a sigma algebra on omega. Let's check this. So the first property is that it should be non-empty. So we see that it already has these two sets present in it. Hence f1 is non-empty. So it satisfies the first property, it's non-empty. The second property is that it should be closed under complement. So each elemental set inside the f1 should also have its complement present in the f1. So let's see, we have the null set phi, it is present in f1, and phi complement should also be present in f1. We can see that phi complement is nothing but omega, and we can see that omega here is present in f1. Hence this satisfies it for second property for null set. Now let's see this as well, the second set, which is the omega. So omega is present in f1, and the complement of omega should also be present in f1. So the complement of omega is nothing but the null set again, which is phi. So this is present in f1, as we can see, this is present in f1. So we can say that it follows the second property as well. So f1 is closed under complement. Now let's see if it satisfies the third property, which is closure under countable union. So we can see that since it only has two elements, like two sets, phi and omega, so the union of both of these sets should also be present in f1. So phi union with omega, which is nothing but omega, should also be present in f1, and yeah, we can see that omega is present in f1. Hence it follows all the three properties. So we can say that f1 is a sigma algebra on omega. So yes, f1 is a sigma algebra on omega. Okay, so this is how we verify whether a set f is a sigma algebra on omega or not. Now let's see another example. So let's say we define f2 as a set of this. So f2 is a set of null set a and b and a, b and c, phi, a, b and omega. And let's see if it is non-empty. Yes, it is non-empty. So the first property is satisfied, that it's non-empty. The second property, closure under complement. So let's try and check this. So this is phi. Phi belongs to f2. Phi complement, which is nothing but omega, which is a, b and c. This also belongs to f2. So this is correct, it satisfies this property for null set. Now let's check if this property is satisfied for the set AB. So this belongs to f2, and the complement of AB would be the set C. But we can see that this set is not present in f2. Hence this f2 is not closed under complement. So since it does not satisfy the second property, the f2 cannot be considered as a sigma algebra on omega. So f1 was a sigma algebra on omega, but f2 is not a sigma algebra on omega. Okay, now let's jump to another example, f3. So this set f3 contains phi, a, b, c, a, b and omega, which is a, b, c. Okay, so let's see if it is non-empty. Obviously it's non-empty, it contains few sets, so F3 is non-empty, it satisfies the first condition. The second condition, is it closed under complement? Let's see. Phi belongs to F3, phi is present in F3, phi complement, which is omega here, which is ABC, is also present in F3. And let's see if the complement for, so we know that A is present in F3. Let's see the complement of A is present in F3 or not. So the complement of A would be B and C, but we can see that this set is not present in F3. Hence, this is not closed under complement. So F3 is also not a sigma algebra on omega. Okay. Now let's jump on to one more example, F4. So this notation here is known as the power set. So this is the power set on omega. So the power set is nothing but it is a set of all the possible subsets of omega. So let's say if omega is 1 comma 2, so the power set of omega would be null set, which is because null set is always a subset of any set, this 1, 2 and 1 comma 2. So this would be the power set as it contains all possible subsets of omega. So in the above example, F4 would be the set of all the possible subsets of omega, so which is null set A, B, C, A, B, B, C and C, A and A, B, C. Here we can see that this is clearly non-empty, so the first property is satisfied. The second property, closure under complement. So let's see, phi belongs to F4 and phi complement, which is omega, also belongs to F4. As you can see, this ABC belongs to F4. Now let's check for this. So for A complement is basically BC, which belongs to F4, as we can see this, and B, the complement of B is nothing but this CA, and similarly the complement of CA is nothing but B. So both of these satisfy this condition. Similarly the complement, both of these also satisfy the condition. And so C, and let's check this for C as well. So C belongs to F4 and the complement of C is AB, so AB also belongs to F4, so this satisfies the condition. C satisfies the condition, and the complement of AB is nothing but C, and C also belongs to F4, so AB also satisfies the condition. And the complement of phi is ABC and the complement of omega is also phi, so both of these also satisfy the condition of closure under complement. Hence all the subsets of, hence all the elements of this F4 follow the property of closure under complement. Hence the second property is satisfied. Now let's see the third property. The third property is the closure under countable union. So we take union of any arbitrary amount of sets. So let's say we take union of, all of these sets. So we take union of phi, union A, B, C, and then A, B, B, C, C, A, and then A, B, C, which is nothing but omega, and omega belongs to F4, so this satisfies. So basically what you need to do is you need to do different permutations and combinations of taking the union of these sets, and you will find that all of such permutations are present in F4. Take any three, let's say this union with C, union with B. This is nothing but omega, and omega belongs to F4. Hence this satisfies. Similarly, you can check this out. AB union A union phi. This is nothing but AB, and AB also belongs to F4. And obviously by intuition you could say that since F4 is the power set, so the power set is a set of all the possible subsets, hence it should be closed under complement, and it should also be closed under countable union. Hence F4 is a sigma algebra on omega, and we can see this as a general rule of thumb that the power set of omega is always a sigma algebra, as it contains all the possible subsets of omega. Okay, so this is pretty straightforward. Now let's create an example. Let's see, we have an omega which is, let's say, 1 and 2. So we want to, let's say we want to create an F such that F is a sigma algebra on omega. So F should be non-empty first of all, for the first condition to be satisfied. So let's say F contains 1. So F contains 1 and some other elements. Okay. Now since F contains 1, so F should also contain the complement of 1. The complement of 1 is the set 2. So F should also contain this for the second property to be satisfied, as it is closed under complement. So F will contain 1 and 2. Now we can see that F should also contain the union of 1 and 2, as according to the third property, if these two sets are present in F, so the countable union of these two sets should also be present in F. So this is nothing but 1 comma 2, which is omega. Okay, so omega is also present in F. Now as omega is present in F, so the complement of omega should also be present in F. Complement of omega is nothing but phi. So phi is also present in F. Now this F satisfies all the three properties. It is non-empty, it is closed under complement, and it is closed under countable union. Okay, now let's say I want to create an F which is a sigma algebra on omega, and let's say I choose a set, an empty set phi. So since phi is a subset of omega, I can have phi present in my sigma algebra. Okay, this, and let's say it has some other sets. So it is, as it contains the null set, it is non-empty. So first condition is satisfied. For the second condition to be satisfied, the complement of phi should also be present in F. So the complement of phi, which is nothing but omega, should also be present in F. So F contains omega as well. Okay, now let's see the third condition. The countable union of all the sets present in F should also be present in F. So phi union with omega, which is nothing but omega, should also be present in F, and it is already present in F. Hence we can say that F which contains these two sets, phi and omega, this also forms a sigma algebra on omega as it satisfies all the three conditions. So we see f, which was the first example was the power set this, and f equals to this. Both of them, sorry, let's make it this. Both of them are eligible to form a sigma algebra on omega. So now I think we can clearly understand the concept of sigma algebra. At least we've got the feel for it. Now let's study some properties of sigma algebra. So the first thing which we can realize is that phi and omega are always present in the sigma algebra. We can see it from our observation as we have covered these examples, and I'll explain you why phi and omega are always present in f. So let's say we have some arbitrary set omega. Okay, proof of this. So let's say we have some arbitrary set omega which contains some elements, and we want to, let's say we want to form f, a sigma algebra on omega. So first condition is that f should be non-empty. So it should contain at least one subset of omega. So it can be a null set, it can be any subset. So let's say the subset A is a subset of omega, and let's say A belongs to f. So A has this subset called A present in it. Now if A is present in the set f, so A complement should also be present in f, as according to the second property, it is closed under complement, so the complement of A should also be present in f. So we say A's complement is also present in f. Now since A complement is present in f, according to the third property, the countable union of both of these sets should also be present in f. So the A union A complement is nothing but omega, so omega should also belong to f. Hence you can see this is the reason why omega is always present inside the sigma algebra f. Now since omega is present here, and we have to follow the second property of closure under complement, so omega complement should also belong to f. So hence omega complement is nothing but phi, hence phi should also belong to f. So we can say that phi and omega should always belong to the sigma algebra f. And let's say you choose an A, set A, such that A is phi itself. Let's say A is nothing but phi. In that case, f would be phi and phi complement, which is nothing but omega. So this is the smallest sigma algebra which is possible for any omega, and it should always contain the null set and the omega itself. Okay, so this is one such property. I have another property, which is that f is closed under countable intersections. So why is that? Let's see. What this statement means is that let's say we have a few subsets of omega, let's say a1, a2 till ak, which are subsets of omega, and a1 intersection a2 intersection ak. Sorry, and I also forgot to mention that a1, a2 and all of these subsets ak, let's say all of them are a part of sigma algebra F as well. So now A1 intersection A2 intersection AK should also be a part of F. So why is that? Let's see. You can also write it in this terminology. I equals 1 to K, AI belongs to F. Okay. Now let's see why is that. So I'll take a simple example. A1 and A2, they both belong to F, and obviously A1 and A2 are also the subsets of omega. Now we can see that it should follow the properties. If F is a sigma algebra, then it should follow all of the three properties. So we can say that A1, A2, let's say we have phi and we have omega and some other elements. So let's see. So since A1 is present in F, so F is closed under complement. So A1 complement should also be present in F. So A1 complement should also be present in F. Okay. Similarly, A2 is present in F. So A2 complement should also be present in F. And the union of A1 and A2 is present in F. So A1 union A2 complement of this whole should also be present in F. If you use De Morgan's law, you will know that this is nothing but A1 complement intersection A2 complement. Okay. And similarly, you can also see that the union of A1 complement and A2 complement should also belong to F, because they follow the third property, closure under countable union, should also belong to F. This is nothing but A1 intersection A2's complement, which belongs to F. And since A1 intersection A2's complement belongs to F and it is closed under complement, so A1 intersection A2 should also belong to F. You can extend it for any number of subsets. So hence we can say that F is closed under countable intersections. Okay, so let's see an example of this. So let's say that omega oops, my bad. So let's say omega is a set this, defined as this. Okay, and let's say I'm preparing a sigma algebra F, which is phi omega 1 and 2 and 3. Let's make a power set 1 2 2 3 1 3. Okay, so F is power set of omega, and so let's see if the intersection of any of these two are present in F or not. So we can check it manually, it's a long way, but taking any of them randomly, let's say this and this, so the intersection of these two sets is 3, and 3 is present in F. Now you can also check it here. So 1 2 intersection 2 3 intersection, let's say omega, so this would be the set 2, and this is also present in F. So you can verify it in a similar way, and you would find that F is also closed under countable intersections if F is a sigma algebra, and you will always find the null set and omega in this sigma algebra. Okay, so we now know a few properties on sigma algebra as well. We know that the power set of omega is always a sigma algebra. We know the three basic conditions which are required for F to be a sigma algebra on omega, and we know that F is closed under countable intersections, and F should at least contain the null set and omega itself. So that concludes this lecture on sigma algebra. I hope you liked the video.